Yes, so again, a very good morning to all of you. So we will start by making some dua first. Bismillah ar-Rahman ar-Rahim. Alhamdulillah Rabbil Alameen. Ar-Rahman ar-Rahim. Maliki yawmiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta alaihim ghayril maghdubi alaihim waladdallin. Amin. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. وصلى الله على سيدنا محمد وعلى آله وصحبه أجمعين. سبحان ربك رب العزة عما يصفون وسلام على المرسلين. Yes, so today's discussion is going to be devoted to first some tutorials, okay, before we will continue with our normal lecture. Okay, I have sent you some slides regarding chapter 4. Okay, so if we have sufficiently solved some questions and then we understand the concept of convection, conduction, then we will jump immediately into the next topic, which is heat exchanger. Okay, so if you look at the first question, okay, so this is question 2, past year question, 2019. So I'm very impressed by some of you. Some of you have already taken the lead by trying to solve the questions on their own. And I'm very impressed by this, by their contribution. Okay, so keep it up. It's very good. Okay, shows how serious you are. Okay, so I hope other students will also follow suit. Okay, so in question number 2A, we are told that describe 3 parameters which determine the heat transfer coefficient of convection between a solid surface and a moving fluid. Okay, so we want to describe 3 main parameters which determine the heat transfer coefficient of convection. So we have already known that convection heat transfer coefficient, okay, is never a property of the solid across which a fluid is flowing. So H depends largely on the fluid properties, namely the density, viscosity, thermal conductivity, and so on. It also depends on the type of flow. Okay, so if the flow is turbulent or laminar flow, then the value for H is going to be different. You understand? So similarly, also the geometry, the shape. Okay, so to give more clarification on this, you see, H is a heat transfer coefficient. H, which is equal to heat transfer coefficient, overall heat transfer coefficient, heat transfer coefficient, heat transfer coefficient. Okay, so we are told that this overall heat transfer coefficient, okay, unlike thermal conductivity, see, thermal conductivity K, it is a parameter that depends on the type of material. It depends on the material across which the thermal energy is flowing. For example, if I have a rectangular solid, okay, if I have iron, okay, iron over here, and then let's say I have also aluminum, Al, and then let's say I have wood. So each and every one of these is going to have different value for K. K for iron will be different from K for aluminum. K for aluminum will be different, let's say K for aluminum, and then the same thing applies to K for wood. Each and every one of these is going to be different. So because this K depends largely on the type of material. Okay, so you and I, we know that aluminum and iron will readily allow the heat to be transported quickly compared to wood. You understand me? So the thermal conductivity for a wood is much, much lower than the thermal conductivity for K. But H is not described in this way. You understand? So H is a parameter, let's say, which is governed by the convection heat transfer coefficient, which equals to HA times delta T. And also, it is a function of the Nusselt number. Say, let's say HL divided by K. This value for all this H does not depend on the material. It depends largely on the fluid properties. You understand? So we will say over here that H, the question says, describe the three parameters which determine the heat transfer coefficient. One of them is the fluid properties. Fluid properties. Okay, so the fluid properties such as density, rho, density, viscosity, and then also maybe thermal conductivity. Okay, so thermal conductivity of the fluid. So these three properties of the fluid, they depend on, they affect the value for H. It means when the density of the fluid changes, the value for H is also affected. If the viscosity of the fluid changes, the value for H is affected. Thermal conductivity of the fluid also changes, then the heat transfer coefficient is also affected. Now the next point is the type of flow or the solid. Let's say I'll say the type of flow. Type of flow. Okay, so the flow, if the flow is laminar flow or the flow is turbulent, so the calculation of the overall heat transfer coefficient is going to be different. Okay, so in the previous lecture, we have noted that for a laminar flow situation, okay, so the Reynolds number will be less than the critical Reynolds number. Similarly, the turbulent flow situation, the Reynolds number is going to be greater than the critical Reynolds number. You understand me? So all of these two situations influence the properties or the value for H. For a laminar flow situation, we have to use appropriate Nusselt number, okay, and which is a function of, let's say, Prandtl number and then RE. You have to select the appropriate number for the Nusselt number to calculate whatever parameters you are interested in. Similarly, the same applies to this one. Now, number 3, you can say maybe the last one, solid geometry. So for the solid geometry, that is the shape. Okay, so if I have, let's say, a circular shape like this, okay, I have a rectangular shape, I have a triangular shape like this. If I have fluid, air flowing across them, I think I have cited this example before. The same property of the air. So the temperature of the air is T infinity, velocity of the air is U infinity. The same velocity flows across these surfaces. Now, assuming if all of these are the same material, such as aluminum, this is aluminum, this is aluminum, you observe that the thermal conductivity over here for number 1 is going to be same as thermal conductivity for number 2 and number 3. So the thermal conductivities are going to be the same. But the value for H is going to be different because of what? The geometry. You understand me? So the heat transfer coefficient for number 1 is never equal to the heat transfer coefficient for number 2. And this is not equal to the heat transfer coefficient for number 3. So that over here, the value for H depends specifically on the geometry. If the geometry changes, immediately the value for H is going to be different. But for thermal conductivity, if they are all aluminum, it means the value for K is going to be the same. K1, K2, K3. They are going to be the same. There is no change because they are the same material. But heat transfer coefficient is going to have a different value, okay, in this situation. Quickly, let us move on to the next question. So we are told again in the next question that a steel pipe is delivering hot water from a cogeneration plant to a nearby stadium for the underground pitch heating to prepare a football match during winter. Okay, so now the pipe whose external surface temperature is 90 degrees Celsius. Okay, so assuming we have a pipe which is laid underground. This is our pipe, assuming. Okay, so the external surface temperature, so the temperature on the surface of the pipe, Ts equals to 95 degrees Celsius. It passes through some open area that is not protected against the wind. So it means that there is air flowing across it. So there will be convection heat transfer. Now the ambient temperature, so T, so also there is air flowing over here. So T infinity equals to 5 degrees Celsius. And the wind flows with a velocity of, so velocity of the wind is given, so U infinity, let's say 8 meters per second, crossing over the pipe. Given the pipe diameter is, so the diameter of the pipe, D, equals to 15 centimeters. Okay, so this will give us about 0.15 meters. Okay, determine the rate of heat loss per unit length from the external surface of the pipe by convection. Okay, so now for a circular cross section, the average Nusselt number for forced convection in cross flow, okay, is given below. So you see, these are the individual Nusselt numbers depending on the flow situation, depending on the Reynolds number. You understand me? So this is a forced convection. Why is it a forced convection? Because the velocity of the fluid is given. You understand me? For natural convection, the fluid has no velocity. You understand me? So the question which we solved previously, I think we have discussed question 3, right? We have already discussed that. Okay, so that was for natural convection. And for this particular question, this is for a forced convection situation. So first thing to analyze this question is to determine the Reynolds number. So the Reynolds number is going to tell us, oh, if the fluid is laminar flow, turbulent flow, or mixed flow situation. You understand me? So that now the basic assumptions necessary to solve this question is like this. Assumptions. Number 1. So first assumption is that it's a steady state situation. Okay, so steady state. Okay, so steady state operation. So it means any parameter that depends on time, okay, is going to be equal to 0. Okay, so, and then number 2, radiation effects are negligible. Radiation effect is negligible. So it means there is no radiation. It means across the, what we mean is that across the surface of the pipe, okay, so because the temperature of the pipe is very, 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 very high, 90 degrees Celsius, there is a potential for the pipe to emit a certain amount of radiation. But we assume that this radiation equals to 0. So there is no radiation. You understand me? So we only have convection heat transfer because of what? Because of the fluid flow. Okay. So now, number 3, let's see. We can say like this, that the air is an ideal gas. Okay, so air that flows across the pipe is an ideal gas. So air behaves, okay, air is ideal gas. Okay, so I think, so the properties of the air at atmospheric pressure, 1 atmospheric pressure, are given. So these are the properties of the air at 1 atmospheric pressure. Okay, so now, next thing, we need to decide what is the flow situation. Is it laminar flow? Is it turbulent flow? Is it mixed flow? You understand? So we need to determine this so that we will appropriately select the appropriate Nossel number over here. Okay, so again, to give you the background of what we are supposed to do, you see, we want to calculate the value for Q convection. And Q convection equals to HA times what? Delta T. Okay, so the area easily we can determine. Delta T also we can determine. Important thing is the value for H. So how do we determine the H? So the general equation for Nossel number equals to H. So now, since we are dealing with a pipe, okay, so we are going to use hydraulic diameter. So it's going to be HD divided by thermal conductivity. If the air were to be flowing across, let's say, a horizontal flat surface like this, then this D will be changed to L. You understand me? So, but over here, we are only dealing with, what do you call it? A cylinder or a pipe. So this should be the hydraulic diameter. So now we have to see there are certain empirical equations that are connected to the Nossel number. And these empirical equations can be determined by selecting or calculating the appropriate Reynolds number over here. If you get the appropriate Reynolds number, then we'll select the Nossel number that conforms with the question. Then we equate that Nossel number to this. Then we can solve for NU. Then consequently, the value for H can be calculated. Then we substitute into this equation. And then here we go, we can calculate the value for Q. Okay, so let us determine first the properties of the air at 1 atmospheric pressure. Means we need to find T film temperature. Okay, so the T film temperature is going to be 95 plus 5. That's the temperature of the air, all divided by 2. So this gives me 50 degrees Celsius. So now we have discovered that our fluid, the properties of the fluid is at 50 degrees Celsius. So it means we are going to select 50 degrees Celsius. Okay? So at 50 degrees Celsius, what are the fluid properties, the density, thermal conductivity, dynamic viscosity, kinematic viscosity, Prandtl number, all are given over here, you see. So we are going to focus our attention on these particular properties of the fluid. Okay, so now let us determine the Reynolds number. So in exams, whenever you determine this temperature like this, write down everything on your paper. Okay, so the density of the fluid equals to 1.0 because you get marks for that. Okay, so then followed by the units, kilogram per meter cube. Then followed by thermal conductivity equals to 0.27, sorry, 0.027, and then 35. Okay, so watt per meters per degree Celsius. And then what else again? We have the kinematic viscosity, sorry, dynamic viscosity, which is given by 1.963 times 10 raised to the power minus 5. And then also last but one, we have the kinematic viscosity, 1.798 times 10 raised to the power minus 5. Okay, so, okay, like this. And then finally, we have the Prandtl number. Prandtl number, PR, is 0.7228. Okay, so all these are dimensionless parameters. So now, quickly, let us find the Reynolds number, RE, equals to, so the velocity of the fluid, which is U infinity, okay, times the hydraulic diameter divided by kinematic viscosity. You understand? So this gives us 8 times 0.15, which is the diameter. Sorry. So let's see. So we have 8 times 0.15, okay, divided by kinematic viscosity, which is this, okay, 1.798, 10 raised to the power minus 5. Okay, so this gives me how much? 66740. So now, if we compare this Reynolds number with the information we have on the table, you see, look over here. So maybe I should make it, enlarge it a little bit. Okay, so anyway, so our Reynolds number is 666,740. So now let's see in which range it falls. So you see it falls on the second, what do you call it? Nozzle number. So means we are going to select the second nozzle number, which is, let's see over here. Oh, sorry, the last one. It's going to be the last one. Though this is 4,000 up to 40,000, but here we are talking about 66,000. So it should be the last one. Okay, so it means the appropriate nozzle number, okay, which is suitable for this particular question, depending on the given Reynolds number, is given by NU. So we have NU So over here we have Nu equals to 0.027 times Re. Okay, so raised to the power 0.805 PR 1/3. Okay, so then this gives me, if you substitute everything into the equation, we will have Nu equals to 0.027, okay, times 66740, which is the Reynolds number, raised to the power 0.805. Okay, times, again, we have Prandtl number 0.7228, 1 raised to the power 1/3. So this eventually gives you 185.35. Okay, so this is our Nusselt number. Now we need to substitute this Nusselt number into the value for N, the general equation. Nu equals to Hd divided by thermal conductivity of the fluid. Okay, so eventually we will have H, which is the heat transfer coefficient, okay, gives us 0.02735 times 185.53 all over 0.15. And this gives me 33.80 watts, okay, Kelvin per degree per meter cube. Okay, so now let us see over here. We have the value for area. So area of the pipe. So area equals to A, which equals to pi d L. Okay, so we know that so far we don't know the length. Okay, so rate of heat loss. So we want to calculate the rate of heat loss per unit length. Okay, so the value for L is not known. So we want to calculate the diameter is known, pi, we know the value for pi, but the length is not known. So we will calculate per unit length of the pipe. Okay, so that's what, but in any case, the area is this. All right, so now we will say over here, our Q equals to HA, okay, times Ts minus T infinity. So, and which gives me the heat transfer coefficient is 33.80. Okay, so times pi. Okay, and then times the diameter, and the diameter of the pipe. Let's see over here. So diameter of the pipe is 0.15. So diameter of the pipe 0.15. Okay, so then and then we know the length. So we don't, sorry, the length is not known. Then we have into bracket 95 minus 5 degrees. So I'll divide this by L, the whole of this by L, and divide this by L. Okay, so this gives us the heat transfer per unit length. Okay, so it means that we will have Q per unit length will give us approximately 1433.3 watt per meters. Okay, so and maybe somebody can help me cross-check this multiplication by pi times 0.15, and then this. Okay, so, but according to my calculation, this is what I got. Okay, so let us move on.
Sir,
Yes.
can we assume length and mention it in assumption?
What?
Can we assume length? Assume the length is
Yes,
1
yes,
meter.
yes. So we can assume the length equals to 1 meter. You understand? So let me look at the question again. It says that, oh, here we are told determine the rate of heat loss per unit length. Okay? So the rate of heat loss per unit length means that your answer should be in watt per meters. You understand? So here you cannot make the assumption for the length. I'm very sorry. Okay, it's because the questions specifically, it says that determine the rate of heat loss per unit length. It's the same as if they say determine the heat flux. So heat flux, what is heat flux? Heat flux is heat loss per unit area. You understand? So same. So heat flux, which is small q, is big Q divided by area. You understand me? So this is heat flux. And the unit for this is going to be watt per meters square. But here the question says determine the heat loss per unit length. So it should be in watt per meters. Is it clear to you?
Yes.
Okay.
Thank you, sir.
Yes, welcome. So any other question before we move on to the next question? Okay, so I'll move on to this particular one. So far, I think I have not solved questions on thermal resistance. So maybe next week, I will look for questions on that. And then we will discuss thermal resistance, rectangular, cylinder, and spherical. Okay, so let us see this question. So there was one student also, again, he tried this question already. I was very happy the way he solved it. Okay, so please let us all contribute like this. Okay, now, according to this question, says that by using an example, describe the significance of what? Thermal conductivity of a material in heat transfer. Okay, so thermal conductivity is the of a material is a measure or the ability of a material to transfer heat fast. Okay, and an example could be a conductor of heat, a good conductor of heat, or a poor conductor of heat. You understand me? So we say that thermal conductivity, by definition, K, thermal conductivity. So this is the solution to this. So thermal conductivity, thermal conductivity. So this question is 1A, 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 question 1A. Thermal conductivity, okay, we say that it's a measure of how fast, okay, it is a measure of how fast heat, okay, is conducted, how fast heat is conducted in a material. Okay, so any good, as an example, is a good conductor or poor conductor. Okay, so, and again, the question is, by using an example, describe the significance of thermal conductivity. Or somebody is just coming. Okay, so, and then thermal conductivity of a material in heat transfer. Yes, so we can say that example like this, and K can either be, K can either be a good or poor conductor. Sorry, poor conductor of heat. Okay, so aluminum, okay, good conductor of heat, and then we will say wood, poor conductor of what? Of heat. Okay, so that's it. Now let's move on to the next question. So in the next question, we are told that we have considered a large plain wall. So we have a plain wall like this. Sorry. So we have a plain wall whose, so in the figure, okay, above, with a surface area is 15 centimeters. So the surface area, A, equals to 15 centimeters square, right? And then thickness, so L, equals to 0.2 meters. That's the thickness. And thermal conductivity of the material is given. The value for K equals to 2.0 watt per meter per degree Celsius. Okay, now the side wall of the material, the side wall is maintained at constant temperature. Okay, side wall. So we can say this is the side wall. T1 equals to 30 degrees Celsius. And then while the right side loses heat by convection to surrounding. So here means there is fluid. We have fluid flowing. So T infinity for this section equals to 0 degrees Celsius. And similarly, the heat transfer coefficient, 40 watt per meter square per degree Celsius. Okay, so now we can say like this, that assuming, let's say, constant thermal conductivity and no heat generation in the wall. So constant thermal conductivity, K is constant, that's the assumption. Okay, no heat generation, so Q dot equals to 0, there is no heat generation. Express the differential equation, and then the boundary condition of the steady state dimensional heat conduction through the wall. Okay, so we have already known that for three-dimensional heat conduction through a plane wall, it is normally governed by 1 over alpha, Okay, so the derivative of dt over the t, this should be equal to the square t over the x square plus the square t over the y square plus what? The square t. You should write down this equation. It should be given to you. The z square plus what? Q, which is heat generation. Okay? Now, based on the assumptions, okay, so first assumption which we also need to add to the question is that, like this, that it is a steady state condition. So for a steady state, SS means steady state. And then the heat is transferred only in one dimension. So the heat is transferred only in one-dimensional axis. So means that only along the x-axis. So we have heat transfer only in the x direction. So it means there is no heat transfer in y and z direction. So again, we are categorically told that there is no heat generation. So eventually, our solution reduces to 1D. So eventually, we'll have d square t over the s square equals to 0. So now we have to integrate both sides. So integrate this. So then we will have, it gives us dt over the x. Okay, so equals to, so we will have dt over the x equals to a constant. So we'll say that let that constant be C1. Again, we integrate again, okay, with respect to x. So that gives us t x equals to C1 x plus another constant again, which is C2. Okay, so now we need to apply the appropriate what? Boundary conditions. Okay, so now boundary conditions are like this. Boundary conditions. So we have at, let's say, x equals to 0. Okay, we know the temperature. T0 equals to T1, and this equals to 30 degrees Celsius. Okay, so now there is one important thing which is we have forgotten. Let's see over here. Yes, so that is it. I think it's correct. So x equals to 0, and then we have T1 equals to this. Okay, so if, let's say, we go by this first boundary condition, another boundary condition is like this, that at x equals to L. Okay, so we are going to have a situation like this. At x equals to L, let me draw the geometry again for you to understand clearly. You see, we don't know the temperature on this surface. So let it be represented by TL. The temperature is not known. But we know that we know the temperature on this side, T1. And as far as heat transfer is concerned, the mode of heat transfer from this x equals to 0 up to x equals to L, this is conduction, Q, conduction. So the same amount of energy, okay, which is transferred to the fluid, that is the air, that is close to this surface. So, and this surface is influenced by convection heat transfer. So here we have convection, Q, convection. Okay, so at steady state condition, we're going to have like this: Q, conduction should be equal to Q, convection. Okay, so now it means that at X equals to L, yes, so this condition is applicable to the state where we have X equals to L. At X equal to L, is immediately the conduction heat transfer is transformed into convection. You understand me? So we can, what is the equation for conduction? Conduction is minus K, okay, dt over dx. And this should be equal to H times the area, okay? And then times we have, oh, I'm very sorry. So we can express it in terms of heat flux, both cases. Okay, so we have minus K dt over dx equals to H into bracket. That gives me T. Okay, so that gives me TL minus T infinity. You understand? So we don't know that particular temperature over here. Okay, so I'm going to take like this, that this gives me TL. Okay, so TL. Okay, so TL equals to this. This is my TL. It's a function of TL. So minus T infinity. Okay, so that is the boundary condition that satisfies it. So at X equals to L, then we have minus K equals to, oh sorry, minus K dt over dx. What is this? So minus K dt over dx. So this pen is misbehaving now. Okay. So let me write it here. So we have minus K at X equals to L. We have minus K dt divided by dx. Let me try again. So we have minus K dt K over dx. So now this should be equal to H into bracket. I'll have TL minus T infinity. Okay, so now these are the primary boundary conditions. So what we will do over here is like this. So for the first one, first boundary condition. So at X equals to 0. So then we will put into the equation, general equation, we have Tx. So we have Tx. So T0. So 1 minute. Yes, so we have over here, so that gives us T0 plus, sorry, equals to C1 times 0 plus what? C2. But we know T0 is 30 degrees Celsius. Okay, so 30 equals to C2. So C2 equals to 30. Now, we need to apply now, similarly, let's say at x equals to L, okay, at x equals to L, I'm going to substitute into the equation again. Okay, so we will have TL. At x equals to L, we have TL equals to, and that gives me TL, and this equals to C1 times L plus C2. That is C2, so it means that over here, TL is given by this. So the value for TL is this particular equation. So wherever I'll see TL, I'll substitute by C1 L plus C2. Okay, so now let's see. Now I'm going to consider this equation, this particular equation. So I'll have minus K, yes, very important, minus K dt over dx. So this thing is starting again. So minus K dt over dx, okay, equals to H equals to H. So we have TL minus T infinity. So wherever we know that the T over the X is equal to C, equals to C, let's see over here. Yes, the T over the X from here, from this equation, the T over the X equals to C1. So we are going to use that. Okay, the T over the X, given that the T over the X equals to C1. Then we substitute into this. So minus K C1 equals to H into bracket. So then I'll have TL. TL is C1. TL gives me C1 L plus C2 and then minus T infinity. Okay, but we know C2 to be equal to 30 degrees, and then we have to determine C1. Okay, so and later on we will substitute into the equation. So eventually, if you rearrange this equation, you will discover that C1 equals to minus H, okay, into bracket C2 minus T infinity, all divided by K plus HL. Okay, so if you substitute the value for H into the equation, you know C2 also equals to 30 degrees Celsius, you know T infinity, then you will get a situation like this. So this gives us 40 into bracket 0 minus 30, all divided by 2 plus 40 times 0.2. Okay, and oh, I'm very sorry. And let me see. So it's a mistake I did over here. So this is a mistake. Sorry. So it's, if you put the value for C1 into, and the parameters for C1 into the equation, let's say you get minus 120. You get minus 120. like this. Okay, so I don't have time to look into the details of this. Okay, so now we will substitute the value for C1 into the equation, then the value for C2 as well into the equation, the general equation. So the Tx, which is a function, temperature is a function of x, gives us, we know that equation equals to, let's see, C1x plus C2. So C1x plus C2. Okay, so then eventually I'll know Tx equals to minus 120x plus C2, which is 30 degrees or 30. Okay, so this is the equation. And you see, so if you want to test it at x equals to 0, T0 equals to 30 degrees Celsius. You understand me? So now we have to find out at x equals to L, what is going to be the temperature. But here we don't know the temperature for TL. Okay, so there is no way we can determine this. So we don't know that. So if we put the x equals to 0.2, very sorry, yes. So we can determine the value for TL. Okay, so and the next question, so this is the first part of the question. Now the next question is telling us to determine the heat flux. So by definition, the heat transfer equals to minus Ka dt over dx. Okay, so and we know this equals to minus Ka. So dt over dx is the same as C1. You understand? So dt over dx is the same as C1. And we have already calculated C1. So this gives me Q dot equals to minus Ka. So my C1 is nothing. It is H into bracket T1 minus T infinity, all divided by K plus H times L. So if you substitute all the parameters into the equation, then you will get 3600 watts. Okay, so or it gives you 3.6 kilowatts. So that's the heat transfer. Okay, so with this, I think I'll look into one other question, and then we can call it a day, or I'll give a brief introduction to, let's say, heat exchangers. Okay, so then next week we will continue our question again on maybe those that I have sent to you. Those questions which are forwarded to you, we'll be discussing them on a daily basis. So we'll do discussion on some questions, and then we'll start with our normal lecturing. Okay, so let me upload this particular slide now. So heat exchanger. By the way, is there any question related to the questions that we have discussed now? Please, if there is any question, let me know immediately. So now let me share a different slide now. So this particular chapter is devoted to heat exchangers. Okay, so what is a heat exchanger? So basically, heat exchanger is a device that, okay, is used to exchange heat, okay, between a hot and then the cold fluid. And there are various types of heat exchangers. So in the industrial scale, we have shell and tube heat exchangers. So you see, very big heat exchangers. Okay, so these are widely used in industrial applications such as steam power cycle, okay, gas power cycle, and so on like this. So all those thermodynamics which you did, okay, condensers of power plants, they basically rely on heat exchangers. Also, the chemical industry, so they also there is also heating and cooling processes over there. Okay, so now heat exchangers can be grouped into two. We have paraflow and cross flow heat exchangers. So in paraflow situation, the hot and cold fluids enter the same end. Okay, so for example, here we have cold fluid entering the tube and then warm fluid entering the shell. Okay, so they are all moving in the same direction along the flow. Okay, so then they exit same direction. So same thing applies to this. So for this situation, the cold fluid is entering the shell, hot fluid is entering the tube. So then they are all moving in the same direction. Then now the temperature profile for the flow situation is like this. For the cold fluid behaves like this. It interacts with the hot fluid. So there is heat transfer from the hot fluid to the cold fluid in this way. So heat is transferred. So it means the temperature for the cold fluid will be increasing, and its behavior is like this. Its temperature will be increasing, and then the temperature for the hot fluid will be reducing like this, in this way. Okay, so this is the temperature profile for both the hot and then the cold fluid. Now, if we come to the counter flow. Counter means that both fluids are moving in opposite direction, okay, to each other. So, but the geometry is the same for parallel situation. Okay, so in counter flow, we have the hot fluid moving inside the shell. Okay, so then again, we have cold fluid again flowing through the tube side. But the important thing is that the warm fluid, it exits, okay, so it exits on this side. Okay, so it goes like this. It goes round the heat exchanger and then comes down in this way. Whereas the cold fluid, it goes through the tube, so its temperature increases gradually, and then it exits the tube. So if you look into this diagram, so as this fluid is moving in this direction, the other fluid is moving in the opposite direction. This situation is what we refer to as the counter flow heat exchanger. And similarly, the heat transfer or the temperature distribution for both the hot and cold fluid is this. So you see, initially at the entry point, the temperature for the cold fluid, let's say T cold, is this. So its temperature initial state for the T cold is this, inlet, and then as it gains or its temperature increases, it will be moving upwards. And then the temperature for this will also be moving downwards. There is no way in which we'll have a crossover of temperature from one side to the other side. So there will always be a space between the two fluids so that there will be continuous exchange of heat between the hot fluid and then the cold fluid. So the hot fluid's temperature will be reducing, the cold fluid's temperature will be increasing in this way. Okay? So this also we have the third one type of heat exchanger. We have the cross flow. And even in cross flow situation, we have the mixed flow, and then we have the unmixed. So cross flow means that the fluid, both fluids will be flowing perpendicular to each other. For example, if you look for this one, the top one, so the fluid, you can take this to be air, atmospheric air, is flowing through this, what do you call it, blades or plates. Okay, now there is a tube that passes through the plates. So these are the tube 1, 2, 3, 4, 5, 6, 7, 8, 9. So these tubes passes through the plate, and we have hot fluid. You can say hot fluid is flowing through each particular tube. So as the cold air flows across the tube, then the fluid is forced to cool down. So it means that this is a cross flow situation. So the cold fluid is moving in this direction, and then the hot fluid is moving in the perpendicular to it. So this is what we call a cross flow situation. For all cross flow situations, the fluid are always made perpendicular to each other. And we say that this is unmixed. Unmixed means that, you see, if we have, let's say, let me explain again here. So if we consider this to be a fluid layer, let's say fluid A, and this is fluid B, and this is fluid C. These three fluids, they do not have opportunity to interact with each other. In other words, fluid A passes through this section and then goes out. Fluid B also passes through this and then it comes out. Fluid C the same way, then it comes out. So they don't have interaction with each other. But if you look into this is what we call a mixed flow situation. In mixed flow situations, all the fluids, let's say this is fluid A, this is fluid B, this is fluid C, they can have opportunity to mix with one another. C can move towards B, B can move towards C, A can move towards C. So they can mix together, and then they eventually come out in a different direction this way. This is what we call a mixed flow situation. So mix does not mean that this fluid in the tube is mixing with the air. No, it's not like that. Okay? So now, next is the most common type of heat exchanger in the industrial application is the shell and tube heat exchanger. Okay, so in shell and tube heat exchanger, we have so many shells. Okay, so we have one shell and so many tubes which are lined up inside the shell. So it means the fluid, it can be hot fluid or cold fluid, is made to pass through these particular tubes. Okay, and then it exits on the other side. Whereas at the shell part, this fluid, it could be the cold one or hot one also, so it's made to flow across these tubes. And we have what we call baffles. These baffles try to orientate the direction of the fluid in different direction so that it creates what we call a turbulence situation, so that the turbulence is going to increase the heat transfer. Okay, so the same thing applies to this particular one. Okay, but let's see over here. Yes, so the same thing applies to this particular one. Okay, and then same thing over here. Baffles are commonly placed into the shell, okay, to force the shell tube, so the shell side fluid to flow across the shell to exchange the heat. Okay, so now let us look at shell and tube multiple pass. Okay, so here we have one shell pass and two tubes. So here we have one shell and two tubes. Here we can have two shell. Two shell means there is a line dividing this. So this is one shell, this another shell. So we have two shells, okay, and four tubes. 1, 2, 3, 4. So these are also different types of heat exchangers. Okay. Then we have plate and frame heat exchanger. This is also widely used in the industry. Okay, so I think I will stop over here, and then we will continue with our discussion for the heat exchanger when we will meet next week, inshallah. Okay, so if there is any question, please let me know. Okay, so if you have anything bothering your mind, you have a question that you would like to discuss, then please let me know immediately. Yes, any questions so far? Okay, so there is no question. All right, thank you very much.